All right, so let's do some couple of problems on IEEE 754 floating point sort of representation. So I know that there's a 32-bit representation and there's also a 64-bit representation, right? So the 32-bit representation or the 32 bits basically are divided into three parts. So you have 1 bit for the sign, and then you have 8 bits for the exponent, and then you have 23 bits for the mantissa. And then for the 64-bit you have 1 bit for the sign, 11 bits for the exponent, and then basically 52 bits for the mantissa, right? So there is that. So yeah, sign, exponent, and then mantissa. And for both of these, like, I mean, I guess I could write the general expression that is used to sort of evaluate them. So you have -1 power whatever the sign bit is, right, 0 or 1, multiplied with basically 2 power whatever your exponent value is in decimal, subtracted with 127, and then that is multiplied with 1 into m, or not 1 into m. This is basically the denormalized, it is the normalized form of the mantissa. I will quickly go over that once to make sure that I actually am clear with the idea of what that is supposed to be. Then again, the 64-bit stuff is basically the same. The only thing that really changes here is this, and that's about it. So instead of so the exponent -127 as it is in the 32-bit, here it becomes e -1023 in the 64-bit version, right? That is basically all it is. And yeah, it is actually pretty simple. Now one thing that I find very fun here is to just go over this nice little normalized part here. So the 1.m into 2 power some e minus whatever k it is, if you look at this, right, for a little bit, you can very easily see that this is basically the binary version of scientific notation, right? I think that is very, very clear and obvious, right? Because I mean, just think about it, right? So you have stuff like it's 6.023 into 10 power 23. You have like 3 into 10 power 8. You have stuff like this, right? So what essentially happens when you are writing things in scientific notation is that you'll have one digit to the left of the decimal point, and then you'll have whatever the other bits are to the right, followed by a power value. That is basically what is happening here as well, right? Look at the parallels, like it's very fun, right? So you have 1.m, which is basically the same thing, and again, if you think about it, binary simply is between not between 0 and 1, it's simply 0 and 1 only. So the maximum value that this place can have here is 1.m, right? It can only be 1. Now, okay, let me be clear with what I mean when I say that. So for example, if a string is 1010, you can write it as 1.010 into 2 power 3. That makes sense, right? Now it could also be, let's say, 010, right? And in that case you would write it as 1.0 into 2 power 1, basically. That is what we are getting at. So clearly you would not just keep 0 here, like 1 makes a lot more sense. Now one thing to again point out here is that you can in fact have 0.m form, and this is actually called the denormalized form. Now this denormalized form is only used mainly when the value is very tiny. It's very tiny. So only when the value is extremely small and like basically 0, like very close to 0, that is when you use this denormalized form. Otherwise we just stick with the normalized form, which is this 1.m thing, right? So that's basically about it. So yeah, this 1.m thing is normalized form of like writing it. So that's about it. Yeah, before I get into the problems, I think now I'm going through all of this by memory, so let's hope that I kind of remember the things properly. So there are some, like, I think 5 special cases, one of which is the this denormalized form that I just sort of mentioned here. So I guess I can just write that down. So one was the denormalized one, which I have basically covered. It doesn't really matter. Now the second one is basically if the exponent bits are basically 0 and the mantissa bits are also 0. In this case it's basically plus minus 0, which is basically 0. So again, that does not really, it's fine basically, right? Then you have the third case, where basically all your exponent bits are ones and the mantissa bits are all 0. Now in this you can have basically two cases. So technically it would be 4 because of the way I am splitting things, but let's keep going. If the sign bit is a 0, that means the number is positive, right? Now just to be clear again, the sign bit will be the first bit, and if the sign bit is 1, it means that it is a negative number. If the sign bit is a 0, that simply means it's a positive number. So that's basically it. Now if the sign bit is 0, that means that it's a very big number that is positive. It is so big and so positive that it's like crazy for the notation to represent it, and therefore it is plus infinity. Makes sense. If the sign bit is 1 and the e's are all like, so the exponent bits are basically all ones, then well, that just makes sense. It's negative infinity. Very obvious. Now there's a fourth case which is also very interesting. So if all the exponent bits are 1, right, and this must be the one where which I think must have been sticking out, because maybe the m can be, maybe some of the bits in the mantissa might be ones, maybe. Now if that is the case, then it is not a number. Now what's very fun actually is that apparently the hardware designers can add certain flags and different behaviors to this mantissa or maybe something else to basically make it so that each of these not a number type errors basically becomes in a sense self-describing, I guess. I don't know how to put it exactly. I don't have the precise information here, but the idea is that, you know, of course it is used to represent things like division by 0, or like, you know, like let's say someone is clever enough to do square root of -1 or something like that, right? So these things are not defined in math, so they're not a number. You try to do this stuff, things go crazy. And so yeah, basically they can design things such that, you know, these will generate basically specific, very specific triggers or something of that sort. Let me make sure I'm still recording. Yes, it's still going on. Okay, let's go and do some numericals, because that is where the real sort of fun stuff is. So yeah, now again, key thing, denormalized form, which is basically this 0.m format, right? And just to be like, I don't know, I'll be a bit verbose here, who cares. So -1 power s into basically 2 power exponent minus whatever the value is into 0.m. That would be the denormalized form of the floating point representation, but the normalized form is basically this one, these two that I've written. That's basically it. Okay, we'll move. It's boring. Let's do the problems. They are so fun. Quite a bit raw, because like I mean, honestly, there's not a lot to do. No, not in that sense, but okay, screw it, let's just get started. So the first problem, which is very fittingly, so we have this hexadecimal, which is 0xCOA, not COA, my brain. This is C0A 0 0 0 0 0. Now the question is, what is this hexadecimal in base 10? Right, so base 10 is of course decimal, nothing crazy, right? So how do we do this? So it's actually very, very simple, and this is very fun. So yeah, let's get started then. So see, what is C in hexadecimal? I think it is 12, right? How do you write 12 in binary? So it is 8 plus 4. So you would write it as 1100, right? That's basically it. 0 is fine. Now A is, I think, a 10. A 10 would be 8 plus 2, which is 1010. Boom, there you go. It's so easy. So now what we will do is we'll take that string that we just had. I'll scroll a bit up so that I can see it. So C0A, and I'm basically going to just write the string. It's very easy. Observe. So C, which is 1100, 0, which is basically 0000, and then you have A, which is 1010, and then you have a bunch of zeros. I'm not going to write all of them. 0000, and then basically goes on. Now again, this is 32 bits, of course, right? There is no need to question this, but of course I will go ahead and bring it up. So let's see the number of let's see the length of this hexadecimal string. So we have 1 2 3 4 5 6 7 8. So you have 8 characters in this string, right? Each hexadecimal string is of the length 4 in binary. So if you do the basic math, so you have 8 hexadecimal values, and each hexadecimal is 4 bits in length. You have 32 bits. Isn't that right? It's that easy. There is honestly nothing else to do, right? So I think if you do 16 hexadecimal bits, you would basically get 64 bits. and why am I drawing that arrow? But yeah, that's the point. We don't, well, there is no need to do 64-bit ones here. They're too big and too massive and too boring. We'll just stick with 32-bit. It's fun, and again, it's quite mechanical once you actually get the hang of it, so let's not worry. Now then, I'll write the normalized form once again. Whoops, let me get a bit more space here actually. So you have minus 1 power s and multiplied with, what was the equation again? I think it was 2e, no, yeah, 2e minus 127 times 1.m, right? Is there, I mean, I guess I could go ahead and explain this e minus 127 part, but I kind of don't see the point of it. uh, I guess I'll just sort of visually show it. So yeah, anyways, and also remember that in 32 bits are a collection of 1, 8 and 23. So we will have 1, this is the sign bit, 1 2 3 4 5 6 7 8. This would, whoops, nope, that is, can't seem to draw straight line. This would be the sign bit, these would be the exponent, and the rest is the mantissa, of course. Okay, so now again visually I think it's very easy to point out that you have 1 2 3 4 5 6 7 8. You have 8 bits here, right? So 2 power 7, the maximum value is 128, and it's sort of riffing off of that. That's the reason why you have this e minus 127. In the 64-bit version you have you'll have, I think, 2 power 10, right? That's basically it. You have 11 again. Let's relate it all back. You see the 8 here. 2 power 10 is the maximum value it can have, right? Or is that a good way to explain it? I don't think it is a good way to explain, so let's undo things a little bit. Okay, so observe, 32-bit you have 32-bit notation, floating point. You have 8 bits for the sign, for the exponent, right? So if you look at the 8 bits, right, you have 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, and finally 2 power 7. So the maximum value you get is 128. We write a minus 1 of that and it's 127. Now it's a good thing here that I finally have to ask myself that why is it not just 128? Why are we writing a 127? I will look into that, but the point is that you write 127. You basically write 2 power n minus 1, where n is the highest bit position that is possible. So here in this case it is 2 power 7 minus 1, which simply becomes 127. Now if you go to the 64-bit notation, I'm going into at so many tangents, but if you go to the 64-bit notation sort of thing, you'll get 1, 11, and then it's 52, right? So it's 1. Now this 11 basically means that the value would be 2 power 11 minus 1. So 1024 minus 1, which is 1023. That is basically the point. I don't have an intuition for why exactly we are doing this minus 1 yet. I think it's a very simple reason, which unfortunately I've not really clarified or looked into, but it's fine. Let's just move and do the problem as we were. And this is a bit of a problem. I scribbled all over the place where I was supposed to be writing the bit values, but okay, I guess I can just copy the string. Yeah, that is probably better. It's anyways a bit too okay. So you have 1100 0000, and then what was it? I think 1010, and so on, right? So we'll do the bit division again, because why the hell not? Whoops, that is, oh my god, I can't write. I can't draw straight lines either. Okay, so you have, that is the sign bit. So 4 and 4, that is the exponent, that is the sign, and this is the mantissa, just as we were earlier. Now you'll clearly notice here that the sign bit is 1. That means that the value that we have is in fact a negative thing. Now the other case that is possible is that we could have had minus 1 power 0 as well, because this sign bit could have very well been a 0, and in that case this would just vanish and become a positive sign, which is fine. We don't really have to go there right now. We will have that in like one of the other examples, I think. Yes, in one of the examples we will definitely see it. Okay, so minus 1, now 2 power. Okay, now this is where we have to do a little bit of calculation. So these are the 8 bits. Come on. Okay, these are the 8 bits. So what is the value stored in E, the exponent bits, basically all the 8 bits? What is the value stored in decimal? So I think if you look at it, it's 128 plus I think 1, so that's 129. Wow, I keep finding the worst place to write all this stuff. So let's do the rough work here. So yeah, as I was saying, 128 plus 1 would simply be 129. So yeah, 129 it is. 129 minus 127, 1 point. Now whatever the mantissa is basically going to come here. Now here's the very funny thing, not a funny thing, but do I bring this up right now? Okay, I think I can bring it up right now, but yeah, sure, why not? So of course the exponent bits, screw it, I you know what, I'm going to consume space anyways. So the exponent bits are basically written in the standard the decimal thing. So basically if you have a string like 0, let me write it with a bit of space. So 1010, you would start from the rightmost and you would say 2 power 0, 2 power 1, 2 power 2, 2 power 3, so on and so forth. Makes sense. Now when it comes to the mantissa, now again remember the mantissa is supposed to sort of represent things that are to the right of the decimal point, right? And so the way it works in this stuff is, whoops, not 2, no, right? If you have something like this, like let's say a string 0110 in the mantissa, it actually is 2 power minus 1. It starts from the left. It doesn't start from the right, as is the case with the regular exponent notation. It starts from the left and the powers are negative. 2 power minus 1, 2 power minus 2, 2 power minus 3, 2 power minus 4, and so on and so forth. Okay, so now if we go back here and if we look at this amazing little string here, you will notice that this is 2 power minus 1. This, however, is 2 power minus 2. So 2 power minus 2 actually is in this whole thing. Now what is 2 power minus 2? Now this is probably not the right way to write it, 1 point like 2 power minus 2, but yeah, come on, just give me some leeway. I think we can write it like that. We are solving stuff anyways. So we will have minus 1 power sign bit 2 power. Now 129 minus 127 simply becomes 2 multiplied with 1. Okay, 1 multiplied with is wrong, but I'll write it like this, 1 by 4, right? Because 2 power minus 2 is basically 1 by 4. Now the way I like to think about this amazing little stupid part here is that this is a mixed fraction. Not yet, this is not a mixed fraction yet, or sorry, what am I even saying? My god, no, this is in fact a mixed fraction. That's what I was saying. Okay, so this 1 by 4 thing that we have is in fact a mixed fraction. So the way I would like basically think about it is, now let's do the evaluation and I'll get to it. So minus 1 power 1 is simply minus 1. 2 power 2 simply becomes a 4. And then you have multiplied with, so 1 by 4. How do you convert a mixed fraction to an improper fraction? So you multiply 4 with 1 and then you add the 1, so it simply becomes 5 by 4. Boom, and you just cancel this stuff and you basically get a minus 5. That's it. So this craziness that was written here, this 0xC0A0000 stuff, is actually 5 in decimal. Whew, isn't that amazing? That's quite fun, if I'm being honest. It's very fun, but all this is very sort of easy nonsense, very boring. So let's make things difficult. Direct conversion is honestly extremely easy. There is and direct conversion specifically from hexadecimal to decimal, that is very easy. But where the real fun lies is when we actually come to the binary part, right? Because there's so much room for error, honestly. Let me do the easier one first because things will get crazy, I think. Let's say minus 1.15625. So I want us to take this decimal string and convert it into a hexadecimal, right? That's basically all that we're doing, and of course it has to follow the IEEE 754 32-bit floating point nonsense, whatever the it doesn't matter, we get the idea, right? So it's this. Now so again 32 bits, right? So 32 bits are again composed of what? So it's the tuple of 1, 8 and 23. So the first bit is of course the sign bit. Now should the sign bit be true? Of course, because look at it, this is a negative value. So therefore we already have a bit of our answer that the sign bit is actually 1. Amazing, we already have something. Awesome, brilliant. Let's move. Now ignore the negative sign. Now let's just look at our little decimal string here. So 1.15625, right? It's this nonsense. If you notice, or if I notice, I can already see that it's already in the normalized form, in a sense. Sorry, what am I even saying? It looks normalized, basically. That is sort of what I was getting at. It doesn't matter, however. You're not going to like shift things around. I don't know why I brought up that normalized thing. That was my brain malfunctioning a bit. But anyways, let's continue. So the way it is supposed to happen now, as you might expect, let me remove this normalization nonsense, because I don't know what I was cooking with that. Sometimes I become stupid. So 1.15625, right? So what do you do here? Very simple. If you think about it, clearly we have to convert this. So look at this decimal. We have to convert things to the right of the decimal and to the left of the decimal to binary. Right now they are in decimal, base 10 notation. We have to convert it into base 2, and then we'll convert it into base 16. That is the point, right? So the idea is you go from a decimal to a binary and then to a hex notation, right? So you go from 10 to base 2 to base 16. Very beautiful, very simple, very elegant, whatever, use whatever words you want. So let's begin. So what is 1 in binary, right? Let's start with that, because of course we'll have to do conversion, right? So how do you convert a number to binary? It's very simple. So you just divide it by 2 and write the remainder at the side, pretending that it divided properly. So 1 is not divisible by 2, of course. So we will write 2 zeros are 0, so it does not divide. And then what is the remainder here? 1. And then that's basically it. We are done. And you sort of write the binary string bottom up. So you will say that if I were to write it down, you would say that 1 in base 10 will be written as 1 in binary. Incredible. Wow, what a finding, isn't it? Amazing. Let's move. So that is half of our work done. Now we move on to the more crazy part, because this is the part that is quite a bit fun. I'll write 0 here because it doesn't really matter. We already have evaluated the 1. We only now care about the 15625. How the hell do you convert this little nonsense to binary? Actually, the point is very simple. So when you have things that are to the left of the decimal, they are already in like whole number value, if you think about it like that. So what we are doing is we are sort of reducing them by 2. Not reducing implies subtraction, but division is in fact who cares? Let's not get theoretical here or philosophical, whatever it is. The idea is that what will happen now is that since the values to the left of the decimal are kind of big, you divide by 2. But since the values to the right of the decimal are like already small, inherently small, you multiply them by 2. So we'll just go with that. Like there is no need to rationalize it and like write some paper on it, but basically that's the point. So we will multiply this string by 2. What is this string when multiplied by 2? Let's take our time. So 2 5s are 10. You write a 1 here. 2 2s are 4. Then that becomes a 5. 2 6 are 12. So that's a 1. 2 5s are 10. So that becomes 11. So that's a 1 1. So 2 2s are 2, and then 3, and then you write a 0 here. Now notice what happens here. What we are supposed to do is we are supposed to take a note of whatever value appears at the left of the decimal point. So here we see a 0. So we will say 0. That's it. And then move on. Okay. So now 0, we'll copy this string here now. So 3 1 2 5. Now notice 0, who even cares? Anything multiplied by 0 doesn't really make any difference. Throw it off, who cares? And you multiply it by 2. Okay. You just multiply it by 2. We'll repeat the process again. Let's see what we get. So 2 5s are 10 again. 2 2s are 4. It becomes a 5. 2 1s are 2, of course, and then 2 3s are 6, and we get a 0. Right? Let me make sure that I'm not making any mistake, because it's very easy to do that. Yeah, seems like we are doing okay. Okay. And again, notice the value to the left of the decimal is a 0, and I am doing all of these live, so I don't really have the solution. So let's hope I'm not making a mistake. Okay, so 0.625 is what we have, so we'll just copy paste that and then multiply that with 2, and what do we get? We get 2 5s are 10, 2 2s are 4, which becomes a 5, 2 6 are 12. Now notice, very fun, you get a 1 here. So what do? You actually write a 1 here, and now you basically subtract the 1 from this 1.250, and you basically end up with 0.25. You multiply it with the 2, and you will get 0.50, right? Which, sure, you will now take this 0, you will copy it here, then you will say that okay, I got a 0.5, multiply it with 2, you get a 1, so you write a 1. Now the funny thing, this is the fun part, 1 minus 1 is basically a 0, so there is nothing left to convert. That's it. We basically converted this entire decimal floating point string to binary. Now how do you read it? Now if it were in fact like a normal value to the left of the decimal point, we would go bottom up That is how we would parse it. But since this is a value that is to the right of the decimal, we go top down. So the binary string actually is now going to be, what is it, 00101. 00101. That is our fractional value. So now if I go and write the string, right, so if we write the string 1.1, what was it, 15625 in base 10, in binary it would be 1.1.00101. That is what it is in binary. But notice again that we again remember the original question. There was a minus on this, and then of course they're asking us to convert it into a hexadecimal thing, which is fine. Let's do that. Whew. Okay, all right. Now before we do any of that nonsense, let us look at this, right? So when you look at this amazing stuff here, you will notice, and again remember the what I think we call it the expression, the form of the whatever the 32-bit thing is. So you have 2 power e minus 127 multiplied by 1.m. So remember this denormalized form, right? So I don't think we have to do anything crazy here, right? This is completely fine by itself. So if you look at this binary string, you will see 1.00, like it basically is already following the denormalized, no, sorry, not the denormalized, it's already following the normalized form. So it is good. We don't have to do anything. But the question then is, what the hell do you do with this nonsense here? Right now, of course, I want to point this out. It's very stupid to fall into the trap that just because I have this little string here, that I'll just bunch it into groups of 4 and then convert it into hex and go home. That would be totally wrong, because we need a 32-bit representation that follows the IEEE standard. This just won't do. So please, even though that seems like it would be a very smart thing to do, it is in fact the most wrong thing that you could possibly do here. Well, maybe not the most wrong thing, but again, let's not get theoretical here. Now my question would be, we should just think here, what should this value even be, right? So if you do regular math, right, generally if I say that let's say my value is 10, how do I write this 10 in a decimal scientific notation? Let's call it that, scientific notation. So you would write it as 10, not 10, sorry, you would write it as 1 into 10 power 1. Of course, that makes sense. But if I were to say don't write it in scientific notation, just write it in terms of power, you would write it as 10 power 1. That also makes sense. Both of these are the exact same thing, right? So this is fine, right? That makes a lot of sense. But now notice, so what this kind of informs us is that if I want a number to be itself, its power should be 1. That is what you would do with regular base 10 notation. But this, what we have here, is binary notation. So if you were to go with the exact same bias that, okay, the power has to be a 1 so that I get the exact same value, and if you were to stick a 1 here, 2 power 1, notice what happens. If let's say my binary string was something like, let's say 0001, so I'm ignore whatever this was, like it looks wrong, I guess, it doesn't really matter, but just understand, right? Let's say this is the normalized form. It's supposed to write something like 0001, which is basically 1. I'm trying to represent 1, but because I have a 2 power 1 on the side, when I multiply it, it becomes a 2. That is stupidity, right? You don't actually want to double it. So that implies that the power of 2 actually has to be 0. Right, a very simple point that I just wanted to be a bit more verbose about, but that's basically the point here, that this 2 power 0, this basically this whole exponent here, 2 power whatever this exponent is, it should be 1, because again notice that we did not have to do anything here. There is no power of 2 here, there is nothing, the power of 2 is 0. I guess I could have started out with that directly instead of going off on this tangent, but I think it makes a lot more sense now, or at least it's a bit more clearer, because yeah, just because there is no reason, to be honest. Okay, so let's see how this would be written. Okay, so the idea was, or the question that we had was, so the exponent has to be 2 power 0 overall. So 2 power e minus 127 in fact has to be 0. Oh sorry, it has to be 1. It has to be a 1, right? So the point here is basically that this whole exponent thing has to be a 0. That is basically what we're getting at. So we will basically get, what will we get? E has to be equal to 127 for that to happen, right? And that's completely fine. We can make that happen. Okay. Yeah, okay, I think we have everything that we actually need. Yes, we do in fact have everything that we need. Okay, so let's bring it all together. So the sign bit has to be a 1, the exponent has to sum up to 127, the mantissa bits are basically these bits which you have to then pad with zeros at the end. So you have 00101, so it becomes 00101, and then you have to add zeros until it becomes like 23 in length. Basically that's the point. So how would you write it out? It's very easy. So sign bit is simply a 1. 127 in binary, this I think would just be us turning on every single switch except that one, right? I mean that does not make sense to you, but it does to me. So 0 1 1 1 1 1 1 1, that has to be 127. Maybe it isn't, who cares? We will see. So 0 0 1 0 1, that is the mantissa. So again, if I were to break it down, this is the sign 0, this is the exponent, and this stuff is going to be the mantissa. Now if I were to actually write it, now of course we have to convert it into hexadecimal as well. So split it into bits of 4. So you would have this as 1, then this as 1, then this as 1, and this as 1. Now this is going to be 0 0 0, and you would have more zeros. Basically that's basically the point. Now what are these values? So this value specifically is going to be, well, what is it? So 1 plus 2 is a 3, 3 plus 8 is 11. I'll just write it in commas, and then we'll sort of fix it. This has to be 16, this has to be a 2, that has to be 8, and then zeros. Whew, okay, so 11 is basically a B, 16 is an F, 2 is a 2, 8 is an 8, and then we have 0 0 0 0, and that there is our string. That is the hexadecimal string that basically is this value. This actually may have been wrong in some way, maybe not, but I do think that this is right. We could check it very quickly actually. IEEE 754 converter. Let's hope I'm not wrong. So hexadecimal, or we could start with this, I guess. So minus 1.15625. So BF94, and then you have a lot of zeros. BF9, whoopsie. B15625. BF94. Did I make a mistake in adding it? BF. Ooh. 1 2 3 4 5 6 7 8. 1 2 3 4. What have I actually done? BF28. BF28. BF28 is apparently 0.6525. Let me troubleshoot here for a second. Okay, turns out that I apparently did not see properly this, that there are 5 ones in here, which was the problem. So yeah, that then basically becomes, I'll just sort of write that again. All of this is wrong, at least the last part is. Okay, so I guess, yeah, that is probably better. Yeah, this is why so you can do everything right and then maybe make the boxes wrong, and you could lose everything. So 4 ones in here, this was the issue, and then you have 1 0 0 1, and then you have 0 1 0 0. That is basically what it was. My god. Okay, so again you have so what was it? 1 plus 2, 3 plus 8 is 11. Here you have an 16. Now here you have 8 plus 1, which is a 9, and here you have a 4, right? That's basically what that string is, and that basically becomes BF94. Was it BF94? I'm doubting everything now. Oh my god, yes, that is right. And then we have 0 0 0 0. So basically the final thing would be 1.15625 in not in binary, whoops, in base 10 is simply going to be 0xBF9400000 in hexadecimal, right? 32-bit floating point, all that nonsense. So that is what it is. This was also quite fun and simple. The only thing was that I messed up with the bit division, because I didn't see that there are 5 bits in a supposed hexadecimal string, which is fine. Okay, let's move. This is the more fun one. Okay, so this is what we are supposed to convert finally. Now I hope none of that mistake happens again, but yeah. This is what we're supposed to do, and again it's supposed to be in IEEE 754 32-bit floating point. You get the story, right? So let's do this now. So again, the value that we have is 13.3, so we'll have to deal with them separately. So let's start. So you start with the 13. So how do you convert a 13 in binary, 13 in decimal to binary, basically 13 in binary? So 2 6 are 12 and the remainder would be 1. Wow. Okay, this is going to be tough with me making stupid mistakes, but okay. 2 3s are 6 and we have a 0 as the remainder. Then we get 2 1s are 2 and we get a 1 as a remainder, and then 2 zeros are 0 and then we get a 1 as a remainder, and then we basically have to parse this in a bottom-up fashion, and we would basically get, 13 in base 10 is simply 1101 in binary. There we go. That's pretty simple. There's nothing crazy there. Now, but what is crazy, however, is 0.3. Now this is where we can easily touch on the idea about why. Just a second, I don't like how I wrote that 3. So this is where we can basically touch on why floating point inherently is complex. So you might see some very interesting stuff as well, like if you do 1.10 or 1 by 10 by 2 by 10, that may not necessarily be equal to 3 by 10. It depends on the precision level, and it also sort of is heavily influenced by basically how precise your notation is really. So you will see now, because binary inherently cannot store these floating point values that precisely because of how it handles things. So let's go. Let's actually just start. So 0.3 multiplied with 2 will get 0.6. Now we'll notice something very interesting here. Let me actually I'll put an arrow here instead. That is probably better. Or actually, you know what, it makes more sense, arrow here and dots here. Okay, 0.6 multiplied with 2, 1.2, which becomes 1. Now again, as we have already seen, so 1 minus 1.2 simply gives us 0.2 into 2, which gives us a 0.4, which gives us a 0, and then you have 0.4 multiplied with 2, you'll basically get 0.8, you'll write a 0 here. Now you notice that things are not really going anywhere. The last time we terminated because we got a plain 0 here, but we are not getting that anymore. Now we have 0.8 into 2, which simply becomes a 1.6, and you get a 1 here. Then you write 0.6 and you can multiply, and you will notice that we are now at 1.2, which gives us a 1, which is great. But then, wait, I didn't make a mistake, right? It looks okay. And then you have 0.2 multiplied by 2, you get a 0.4, you get a 0. You can basically keep going here, and this will not terminate. And that is the point, that because this notation is just so forcing using 2 for everything, it cannot handle stuff like this very accurately. It will just keep going on and on and on, and that's the fun thing. But what you'll notice here is that it does in fact start repeating. So if we look at this, these values that we have here, right, you will notice that you get 1.2 here and you get a 1.2 here. So essentially what is happening is stuff until here is basically unique, right? Because after that I think everything is kind of the same. Or is it? Okay, hold on. So yeah, stuff from here to here is unique, but from here onwards it's basically everything is repeating, right? You get 1.2, you got a 1.2 here, you're getting a 0.4 here, you got it already. And if we continue, we'll actually just get 0.8, right? We can just continue and sort of feel it. 0.4 into 2 will simply give us a 0.8, which is a 0. Then 0.8 multiplied with 2 will give us a 1.6, which gives us a 1. and we can basically continue, right? So notice again, I'll now get 0.6 into 2, which will give us what is it, 1.2, and we'll get 1 here. And sort of notice how basically this whole thing is repeating now, and it's kind of boring. So we don't want to unnecessarily capture too much nonsense. Then we get it that basically this string here will repeat over and over again. So we'll just parse it, we'll take this part and we'll sort of write that okay, this thing is supposed to repeat. So the point that we got here is that 0.3 in base 10 would actually be something like, what was the binary string again? 01001. So 01001, is that it? 0101001. Yeah, 0100. I want to make sure I'm not making any mistakes here, and I'll put a bar here. Now the bar is basically the point is, you know, when you write things like 0.9 bar, it is supposed to mean that it sort of goes on up to infinity, and there's like a infinite number of nines. Essentially that's the point. That is what I'm trying to write here as well with this bar. Okay, amazing. Now another thing to note here, I didn't point this out when we started. Look at this number, it's not negative, which means that the sign bit is actually going to be 0 this time, which is fun. So sign bit will be 0. We could have anyways found this out later, but I kind of was itching to point that out. Okay, so 13. So again, the value that we had originally was 13.3. Now if we write this thing in binary, right, if we just try to write it in binary, this is what it would look like: 0 1 0 0 1, and then put a bar over that. I don't know if this is legal to write this bar over that, but who cares? Again, the point is to just do our work here. Now you'll notice something very, very interesting. Earlier, when we were doing the 1.16, that one, when we were doing this, we already got it in this notation where we had a 1.0010. It was basically normalized already, but this thing isn't normalized. This is a very big value, right? This is too big. So what we have to do is basically we have to shift this decimal here. It has to be here right after the first one. So how do you do it, right? So I think we can just take some very simple examples. So 1 2 3 4, if I want to write it as if I want to write 1 2 3 4 as 123.4, I will write it as that and then say that I need to multiply it with a 10 power 1 to actually get the original string back. That makes sense. Now if I wanted to write it as 12.34, I would then say that buddy, multiply it with a 10 power 2 and you will get the original string back. If someone told me no, I want to write it as 1.234, then I would say to them that look, you have to multiply it with a 10 power 3 and then you will get the original string back. That is the point. So basically what happens here is that we are going to take this guy and we are going to shift the decimal dot basically, or decimal point to the left, doing this thing, but in base 2. This is again base 10, since our number system is in base 10, but we have to do it in binary. That's basically it. Very, very simple. Let me get a new page and we will start. So let me just copy the string once. So 1101.1101.01.01001. Okay. Now if I were to convert this, how would it work? So we have to basically shift the decimal place 3 places. So I would write it as 1.101 into 2 power 3, right? That makes sense. This is how it would actually look like. Now of course we are ignoring this mantissa part for now, I know that. In fact, you know what, let me be a bit more precise. Screw this, we'll be more precise. I'll write it like this. So this would actually become 1.101.01001. Let me not get lost. 101. Yeah, this is how the mantissa will actually look. So this part will actually keep on repeating, and this is how it would look. And in order to sort of tell the machine and whatever that look, actually this thing is supposed to be this value, we will multiply 2 power 3, right? That's basically what is happening. Nothing crazy there. That's it, right? But now you're faced with a very interesting problem. This guy will not stop repeating ever. Like it'll just keep going on, and because of that we are basically cursed. We are supposed to take care of this guy now, because otherwise our calculations will be imperfect, and if you do like basically a lot of calculations and you don't take care of this recurring part, you will be screwed. Basically the math will be inaccurate. But before we do that, let's take care of a few other things. So again, as I mentioned earlier, sign bit is 0. Now the exponent has to turn out to be a 3. But remember how the exponent thing is actually written. It's 2 power e minus, no, okay, that might confuse, let's call it k minus 127. Now notice again that since we actually want it to be equal to 2 power 3, this k minus this k minus 127 thing has to be equal to 3. So k in turn would actually be equal to 130. That's it. So our exponent bits have to sum up to 130, right? That's it. Now I can already also split it up and say that 130 is basically 128 plus 2, but we'll come back to that later. Okay, and now the mantissa. You know what, let's keep that in mind. I will not deal with it right now. Let's start writing the bits. So sign bit is a 0, very happy. Then 128 plus 2, so 128. So 1 2 3 4 wait, 1 2 3 4 5 6 7 8. My god, I feel lost. I think this is it. 1 2 3 4 1 2 3 4. Yep, that makes sense. Okay, so let me just be very precise here. So this is the sign bit, this is the exponent bit. Now we have to write the mantissa. Now this is where the sort of nonsense begins. We have to copy this string first. So you have 1 0 1 0 1 0 0 1, and now notice we have to repeat this whole nonsense a few times. How many times exactly? 23 times in total. Not 23 times in that sense, but up to this length being 23. Right, so this is the mantissa part. How many bits do we already have? 1 2 3 4 5 6 7 8. We already have only 8 bits, and we have to basically add like 15 or something more, right? It's a crazy world, but we have to do that. So 0 1 0 0 1. How 1 2 3 4 5. So basically I have to write that 2 more times. 0 1 0 0 1 0 1 0 0 1 0 0 fuck 0 0 0 1 0 0 1. Let me just count again. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23. Awesome, but we are not done. See, this is the sad part, because you have to accept the reality. Now we can't just be lazy and call this our notation. Of course we have to convert to hex. I'm not talking about that. I'm talking about the fact that we are not caring about this recurring part, but we actually have to care about the recurring part, because it does in fact repeat again and again. Okay, so what that means is that we can't just stop here. So I want to sort of bring in another simple sort of thing that we do in science in general. So where can I write this? I guess I'll just write here. So when you have something like, let's say 2.71, I tell you, you know what, I don't want the decimal values. What do you do in general? You call it a 3. Makes sense. What is this? This is rounding up. If you have a value that is like 2.01, I tell you I don't want the decimal, drop it. So what do? You call it a 2. Makes sense. I tell you I have a 2.00, I don't want the 00. What do you call it? You call it a 2. That also makes sense. Now what do you do if you have something like 1.5? Let's play around for a little bit. So if you have 1.5, the idea is that when it comes to rounding off or rounding up, down, whatever it is, you look at the decimal value. So it's a 5, we are at the middle. Then you look at the left side, basically the whatever the value is over here, right? And you say that since it is odd, it should become even. So you would represent it as 2, basically. That is how that works. So if you have something like, let's say 2.5 on the other hand, you see a 0.5, so you see a 5 here, you see a 2, you say that it's already even, therefore it does not have to be rounded up, it will sort of stay at a 2. The point is basically that we round up or down so that the number stays even, basically, or becomes even at the very. If it's odd, make it even by rounding up. If it is even, do not do any rounding. Okay. Now the problem with this this mantissa that we have is that this thing is going to repeat again and again. So let me just capture the last few bits. So 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 Oh, okay. Now again, I know that this is in fact not accurate because there will be more bits. Sorry, not more bits. The idea is that you'll have 4 bits here, 4 bits here, and the 3 here and then 1 here. That makes it a proper hex string. Doesn't matter. Don't worry about that. If you look at the string, the way it continues, it is a 0 1 0 1 0 0 1, right? 0 0 1. This is how it continues. So if you think about it, this is how it is: 0 0 1, and then we sort of are breaking here, but then this nonsense will repeat after a while. Now the way you can think about it is that it did so since if you look at these parts here, now there's 2 or 3 bits here actually. There's a sticky bit, there's 2 more bits. I'm forgetting the name, which is very unfortunate, but the point is that you look at this bit and you look at these 2 bits basically, or these 3 bits, 23 24 25, or I think it is 24 25 26. Again, very blurry on it. Maybe I'll do another video where I'm actually going over these kind of horrible numericals where you have recurrence, because this is actually quite important, right? Floating point precision is very important. But yeah, basically the point is you look at, I think, these 3 bits, and then you basically decide whether to round up or round down. Now here you will notice that if you think about it, 0 0 1 and everything keeps going on, in a way you can kind of drop all of this and round it up to a 1. We are just taking an OR of all the digits. We're saying that what, somewhere down the line there is a 1, and there are 1s, so screw it, we'll consider this to be a 1. So now the reality is that now you are saying that you have 0 0 1 and then at the end you have a 0 1 1, right? But the idea is that you look at this digit as well, the one that is right after the 23rd bit, the 24th bit. The 24th bit is a 0, right? So what that means is that if it is a 0, it means that whatever this value is less than 0.5, which means we don't have to worry about rounding up or down, because think about it, if you have 2.35, you will simply call it a 2 if you want to round. You won't care, you'll be like, screw it, I'm happy with the 2. But if it is 2.75, you'll be like, okay, I need to round it up to 3 now, right? That's how that works. So we can be happy here. Now if it was something like, let's say 0 0 1 and then 1 1 1, now, or 1 0 1 even, let's call it that. So here, because it is a 1, this means that it is right at a 0.5. This is basically 0.5, and then you have to look at these values and decide whether it is going over the 0.5 or not. And here it actually is going over a 0.5 if you think about it, right? You are adding some value here. 0 1 is actually not insignificant. It will add something, it will add some x, which will make it, which will make this k value greater than 0.5, and therefore you will have to round up. Now here it seems like luckily we don't have to round up. I could be wrong, maybe I made some mistake while doing the decimal thing. It is entirely possible, because now I kind of lost my confidence after the previous one. But yeah, basically this is the string, and we have to essentially start converting it now. Now give me the eraser for a second. I'll remove these dashes so that I can actually work again. I kind of don't know what the cut, paste or copy tool is in this editor. Very new to all this, so yeah, can't copy paste things, and I don't just want to erase all this stuff that I wrote here. Well, maybe I'll erase this part. I don't need too much space, but I do need space. Okay, so here we go. Okay, now let's deal with it. So our representation is actually going to be, so 0 1 0 0, this is actually a 4, that is a 0 0 0, that looks like a 1, yeah, that is a 1, that is a 2, and then this looks like a, what the hell is that, a 5, that is a 5, and then this is a 4, this is a 4, and then this is a 2 plus 8, which is a 10, 2 plus 8, which is a 10, and then this is a 5, then this is a 4, or wait, is it a 4? 0 1, no, that's a 2, shit, that is a 2, that is a 2, and then this is a 9. My god, weird, huh? Let's just make sure, yeah, okay, I think I've done things properly. Now let's convert it into hexadecimal. So 4 in hexadecimal is simply 4, 4 2 5 4, that's amazing. 10 5, okay, so this is where we kind of have to write stuff. A 5 2 9, yeah. So that is what we are getting, 0x454254 A529. Okay, let's check it out, because I'm kind of worried that this might actually be a bit, off by some values, I guess. So what did I find again? So we have 4254 A529. Okay, this is actually crazy. So that is incredibly wrong. Wow, where did it all go wrong? Okay, let's just see. 132. Wait, that looks wrong. Yeah, that is. Wait a second. Seems like I made a mistake while counting the length, in a sense, of the binary strings. 1 2 3 4 5 6 7 8. You know what I could do? I could simply just take this, and I could just do like the ticking procedure here to just check if things actually went wrong. So 1 0 1 0 1 0 0 1 0 0 1 0 0 1, which was here, 0 0 1 0 1 0 0 1. My god, I'm getting lost. 0 0 1, I think this was 0 1, which is right. Then 0 0. Wait, is this supposed to? Oh, okay, not that one. 0 1. Yep. Then 0 1. Yes, 0 0 1. Okay, that basically is it. 13.29. Okay. So my final answer was wrong because I probably like made a error while parsing. We'll fix this. But basically, if you look at the decimal notation that I got, it's pretty much quite accurate. So that's there. Now I will not rest, however. I need to find out what mistake I made here. So give me another attempt at this. I'm going to write the binary string again and parse it again. Because let's come on, we can't be so close and then give up. That's not how this works. Okay, so again, where were we? Okay, so sign bit was a 0. So sign bit was a 0. The exponent is supposed to be a 3. So I'll just add 127 here. We'll get a 130. 130 is again 128 plus 2. And then the mantissa 101 101 101 101 01001 0101 01001. Okay, I'll keep that in mind. We'll just move now. Whew, okay, so let's do this properly this time. Now I'll just write the string. Actually, that is better. Yeah, there we go. That's much better. I'll keep it written this time. So 0 1 0 0. So that's 3. I have to write these 4. 0 0 0 1, which is that. Next we start from here. 0 1 0 1, which is that. Okay, and now from here we are starting this recurrent nonsense, which is, so 1 2 3 bits are already done. We have to do like 5 more. 0 1 0 0 0 1 0 0 1 0 1 0 1 0 1 0. Okay, then 0 1 0 1 0 1 0 1 0 1 0 1. Then you have 0 1 0 1. Then you have 0 0 1 0. Sorry, 1 2 3 4 5 6 7. 0 0 0 1 0. Then you have 1 0 0 1. Okay, let's evaluate this now. Whew, okay, so this is a 4, this is a 1, this is a 1 plus 4, a 5, this is a 4, yes, this is a 10, this is a 5, right, this is a 2, this is a 9. Okay, so 4 1 5 4 A 5 2 9. This is what I'm getting now. Let's check once if this is actually what the notation is. So 4154 A529. Yes, I did in fact get it this time. So I guess I just need to work on sort of writing the notation properly and splitting it down properly. Maybe that is the thing, right? Maybe break it into more modular parts and then do the numerical. But yeah, that's basically about it. And you can see very clearly that this whole notation thing is quite very accurate, even though, you know, of course there is a bit of error happening during the conversion. So yeah, there's definitely that which is happening. Now let's check if rounding up would have helped. Maybe I made a mistake, but no, it doesn't seem like it is making that much of a difference. So yeah, you can see very clearly that this stuff works quite very well. And yeah, that was basically it. I may do a couple more problems. This stuff is quite fun actually, even though I kind of suck at it. But yeah, that's about it.